Hi, welcome back to this video series on cryptography. Today, I will continue my discussion on quadratic residues. In this segment, I will show you how we can generate random numbers using quadratic residues concept. We can use these generated random numbers for cryptographic applications like key generation or generating IVs and so on. Let me start giving you the motivation behind this approach. Suppose you have a small seed, okay? Maybe you have a hardware random number generator that was able to generate a random number X, right? Which is say of size 2048-bit, right? So it's made of 2048-bit number. But suppose your goal is to produce a very, very large random number, okay? Well, you could try to use the hardware random number generator, but it may be slow. You may not have an easy way to generate a large volume of random numbers. So the idea is to use quadratic residue concept as follows. As simple as this, actually. Suppose X is a quadratic residue. You do X square mod N. Okay, that's all. And this becomes your generator. So let me write it more formally. I will explain what I means in a moment. So your I plus 1th term is nothing but the square of the ith term, right, in mod N, where N is a composite number. They proved that this is cryptographically secure with the assumption that given a number N, composite number N, it's difficult to find the prime factors, and it is difficult to tell whether a number X is a quadratic residue or not. Okay, that's very informally. That's basically the theory behind this generator. So it's BBS generator. Okay. All right. So let me now talk about this formula more precisely. What is I? I can be anything greater than or equal to 0, integer, right? So, but the question is, what is x0 then? X0 itself is a quadratic residue, right? So it must be a quadratic residue. How do we get a x0 which is a quadratic residue? The trick is, suppose you can just select an x0 randomly from Zn star group that we talked about earlier and just square it. And now you have your generator ready. Okay, what is N then? N is a composite number made of 2 distinct primes, but it has more structure, okay? And that structure is needed for a different purpose that I will explain in the different segment. For now, just assume that N is made of 2 primes P and Q, right? This is the structure of your prime P and Q, all right? So such a structure together with an x0 which belongs to a quadratic residue set, right, gives you a very nice random number generator with a number theoretic assumption that it is difficult to factor N, very large N. Given N, it's difficult to find P and Q. Okay, so so what is the randomness property here that we are talking about? The only thing from a generation point of view is that you need to be able to generate a small number x0, right? X0 must be, it's x0 as a seed, and x0 must be a quadratic residue, and it must be a random number to start with. Okay, that maybe there is a hardware you have that can generate 2048-bit random number, okay? Through some atmospheric noise or some kind of a mouse movement, whatnot, right? You get an initial seed, and then you can generate very large number of random bits. For example, suppose your goal is to generate a sequence of zeros and ones. What you will do is you will just take your xi plus 1, right, and do mod 2. Then you will get a bit. So by doing a mod 2 on this xi plus 1, you will get the next bit, and then continue this. So you'll get a sequence of zeros and ones. All right, that's basically the core idea of this Blum-Blum-Shub vector Shub generator. Okay, I will show you some examples to get this idea across. I'm not going to tell you how I got my N. I just generated a very large N, 2048-bit N. right? But then I'm going to show to you that I can generate very, very large random numbers easily using this BBS generator scheme. Okay. All right, let me continue now. News share. The scientific paper is this new simple unpredictable pseudo random number generator. Okay. The paper introduces two generators. One is 1 by P generator, which is a pseudo random number generator, but it is not unpredictable. So it's not necessarily good for cryptographic applications. But then the second generator, X square mod n, that we just talked about, is indeed unpredictable from a cryptographic perspective. Okay. All right. So I'm going to now show to you a simple demo of this application of this random number generator algorithm. Okay. So as I mentioned earlier, I have my n, very large n, generated by just sampling P and Qs. Assume n was given to us. Okay. N is a large data, right? 2048-bit number or something like that. So I'm going to just use that technique now. So it turned out that I will show you how I got the n as well. Okay, so here is my, let's assume that the n is somebody's public key. Okay, they know the P's and Q's, but we can use their n to generate a sequence of random numbers. Okay, that's what we are going to do. So I wrote this little program, right? It's called random bits algorithm, right? You specify the n, the capital N is shown in program as small n because usually variable names are small. And then we specify how many bits do we want to generate. Say, for example, the goal is to generate, say, a 30-bit number, okay? So what I'm going to do, or 50-bit number, whatever. So let's do that first. Let me not use this for now. Let me just keep it simple. And I'm going to just run it. So you see here, I got a bunch of random number generator right away. We can increase. Suppose I want 500 bits. Very quickly get 500 bits. 5,000 bits very quickly. So there are some very nice mathematical properties built inside this generator. The period of this algorithm, meaning when will it repeat? If you remember the formalism, right? We talked about xi plus 1 is congruent to xi square mod n, right? Of course, at some point you will have collusion, right? Why is that? Let me take a simple example. Suppose your group that you're working with is, say, n is equal to made of 2 prime numbers with this particular property. Let's say my n is 33, okay? Which means my P is 3 and Q is 11, okay? Okay, my P and Q satisfies this constraint, right? What are the quadratic residues? We talked about this group earlier. The quadratic residues are a set of numbers that can be written as power of 2, or so these are the quadratic residues of this particular group, okay? Because they can be represented as power of 2. All right, so we can actually try that online on my program. From my quadratic residue, we will import my routines and we will do 33, right? Whatever I wrote comes from the second column, okay? All the numbers that you saw, 1, 4, 16, 25, 31. That's basically the set of numbers that are basically quadratic residues of this group C star 33. Okay, so now if you create a map as we did, like let's say our map is assuming a function f of x is equal to x square mod n. Okay, what can we say about this function? F of x is equal to x square mod n. This function is a 1-1 function. Okay, if we restrict our domain to be in the set of quadratic residues, right? Then we have quadratic residue mapped to another quadratic residue, okay? We can actually confirm this and test it for ourselves. For example, if remember the quadratic residue in this scenario for this particular group are the numbers 1, the second column of this table actually, 1, 4, these numbers can be represented as power of 2. 16, 25, 31, right? These are the quadratic residues of group Z star 33. Okay, so if you take any number here and square it and take mod n33, you will get back again an element in the set only. So that's the reason we say this is a one-to-one function. Okay, every element has only one. If you square it, you get 1. If you square this, you get 16. If you square 16, 16 into 16 is 256. And if you divide that by 33, you get 25 as a reminder. Okay, and if you take 25 and square it and take a remainder with 31, after dividing it, you get 31. And then for 31, you get 4. So as you can see, this is clearly a one-one function, no collusion whatsoever, right? Each element in the quadratic residue gets mapped to another unique element. Okay, this is only because of n being made of 2 primes p and q with certain property that p and q are both 3 mod 4. Okay, so given this context, now suppose you start your random number generator by randomly picking an element from quadratic residue, right? Say, let's assume you picked your x0 to be 16, right? What will be your sequence? Your sequence will be 16 mapped to 25, which is the next element, right? Because you're doing square, repeated square. And 25 maps to 31, and 31 maps to 4, 4 maps to 16. Now the cycle is directed, right? Because you are now back to 16. So this is basically what I mean by cycle. So far, 16, 25, 31, 4, there's no cycle. After that, the cycle will continue. Okay. The question now is, for large n, let's say n being 20, 48-bit number, what is the cycle length? Because you don't want the random numbers to repeat, otherwise the cryptographic system may fail. So, but mathematically it will repeat if you keep on doing x square mod n, because that's because of the property of the algebraic structure. Okay, so any one-to-one function, if you keep on jumping from domain to range, you will eventually hit the cycle. So what the researchers have proved it for large numbers, you can have very, very large cycle. The point of this session is to show to you very quickly that this very, very simple quadratic residue concept has enormous applications in cryptography, and we can generate from a small seed made of, say, if you treat this x0 to be seed, right? X0 can be treated as a seed. The seed length is just 20, 48-bit number. You could generate very, very large random sequence of zeros and ones. All you have to do is do x square mod n, and then do a %2, meaning get the last 2 digits, right? Last digit. Okay. By doing a %2, you get the parity bit. Okay. So here is the quick summary of the algorithm, right? You can, if you know the n, and you know how many bits you would like to have, you need, of course, a random number generator that can pick a random element, which is the seed element, right? This is the seed. So the seed is basically an element in the quadratic residue. So x square mod n is the seed. And then all you're doing is you're basically repeating this algorithm, right? Keep multiplying your seed by itself. That means you are doing square, repeated square. And if the goal is to generate bits of only bits of zeros and ones, of course, then you take your seed, current seed, and do a %2, right? That will give you the parity bit. Okay, this is it basically. This is the algorithm. Of course, you may say, well, you still need a random number generator to help you to pick an element x. That's true. There you can assume you have, say, some kind of a hardware random number generator that will pick a random x for you. That's the only thing you need. And then you can generate very, very large sequence of zeros and ones. In the next segment, I will show you how you can use this for public key cryptography. Okay, and I will show you that how one sender can encrypt a large volume of data using this key that was generated using the BBS scheme, and the receiver will be able to decrypt if he or she knows the prime factors of n. Okay, that's basically the goal for the next segment. Okay, thank you very much for your attention. That's all.